All right, so today we're diving into something pretty fascinating, something called propositional dynamic logic, or PDL for short. And, you know, thinking about our listener, I bet with their philosophical mind, they've spent some time thinking about how we reason about actions and consequences and how that all plays out. Well, PDL, you can think of it kind of like a formal system to do that, but in the world of computer programs, it gives us a way to really analyze what holds true, before, during, and after a program does its thing.
Yeah, that's a really great way to put it. I think from a philosophical perspective, what's really cool about PDL is that it brings in this idea of logical necessity, like what must be true, and possibility, like what could be true, tied directly to these actions, these programs. So for every program we can think up, PDL basically gives us a way to make a modality, a logical concept out of it.
Exactly. And you know what? The notation they use for it, it's actually pretty elegant, like deceptively simple. Say we have a program and we'll call it alpha, that's the Greek letter alpha,
hmm
and we have some statement about what's going on in the computation and we'll call that A. Well, when you see alpha, what that means is after every single possible way that program alpha could finish running, the statement A will be true. So it's this really precise way of saying, okay, if we run this code, this is what's going to be true no matter what.
It's really interesting when you think about where this whole idea came from. It wasn't just like somebody just popped up with it out of nowhere. You can trace it back to people like Engler, Hoare, and Yanov, these real pioneers who were really wrestling with this problem of like, how do you formally describe what algorithms do? And their work kind of laid the groundwork for these more powerful systems like algorithmic logic and dynamic logic. But like we said, today we're zeroing in on PDL, this sort of streamlined version, really hammered out by Fisher and Ladner.
And why PDL specifically, right? I think for one, it really gets at the core of dynamic logic by focusing on propositions, those statements that can be true or false, instead of getting bogged down in like first order logic with objects and quantifiers and all that. This lets us break apart these fundamental logical structures that pop up when you start thinking about computation as like hopping between different states. So in this deep dive, we're going to try to make it super clear how PDL ticks, what the main parts are, and why it's actually a pretty big deal if you're interested in the logical side of computation, and frankly, any system that changes over time. I know our listener with their philosophical background is going to appreciate how rigorous this whole structure is and just what it means for understanding what programs are and what they do to these abstract states in computation.
So if we're going to do this right, we got to start with the absolute basics of PDL. That means the syntax, like the grammar, how we write meaningful statements in this logic, and then the semantics, which is how we actually figure out what those statements mean, like whether they're true or false. At its core, PDL is all about two main things: propositions and programs. Propositions, think of them like little snapshots that tell us something about the system, and they can be true or false at any given moment. Programs, on the other hand, are the actions that can actually change those snapshots, change the state of things.
Right. So we start with a bunch of basic propositions, the simplest ones, which we call atomic propositions. And then we have a set of like fundamental actions or atomic programs. These are the building blocks, right? From there, we can build up more complex formulas, the stuff that we can actually say is true or false by using those logical connectors we all know and love, like not written as this symbol and or written as lore. But the real magic of PDL is this modal operator alpha, where alpha stands for a program like we talked about before.
And just like we can build up these complex logical formulas, we can also stick together atomic programs to get these more elaborate programs. There are a few ways we can do that. First, we've got what's called sequential composition. That's written as alpha, beta, and basically means do program alpha, and then once that's done, do program beta. Then we've got non-deterministic choice, alpha beta, which basically means we're picking between alpha or beta, but we don't know which one's going to get picked beforehand. It's kind of like a fork in the road.
And then there's alpha, which stands for unbounded iteration. Think of it like do program alpha over and over again, but we don't know exactly how many times beforehand. It could be 0 times, it could be 100 times, who knows? Finally, there's the test, written as A, which is like a little if statement. It says, if proposition A is true right now, then keep going without changing anything. But if A is false, then stop right there.
Okay, so we've got the building blocks, but we need a way to actually give them meaning, right? So we use these things called labeled transition systems, LTSs for short. Imagine it like a diagram of a little machine. It's got all these different states the machine can be in, and then arrows between the states that show how the machine can move from one to another. And each arrow is labeled with an atomic program. It's kind of like those Kripke models you might have seen in modal logic. But instead of just any old accessibility relation, we've got these specific actions, these programs that cause the transitions between states. We also need to say which of our atomic propositions are true in each state.
So we have this mapping, we call it, that takes each atomic program, we'll call it pi, that's the Greek letter pi, and it gives us like a set of pairs of states. If you have a pair in pi, it means you can run the atomic program starting in state, and you might end up in state y. And then we've got another function that tells us for each atomic proposition, all the states where it's true.
And we can use these basic mappings to figure out what more complex programs and formulas mean. So for example, we can say XR alpha beta is true if there's some middle state, let's call it Z, so that running alpha from X could get you 2, and then running beta from Z could get you to Y. And for non-deterministic choice, alpha beta is true if either alpha can take you from X to Y or beta can.
For iteration, we say XRAY is true if you can get from X to Y by running alpha some number of times. Could be 0 times, could be 1,000,000 times, doesn't matter as long as it's a finite number of times. For the test, X and Y are actually the same state, and the proposition is true in that state.
Now for the formulas, we figure out whether they're true or false based on the LTS. Like the formulas means false. It's not true in any state. So the set of states where it's true is just the empty set, nothing there. No, not A is true in all the states where A is not true. L or B is true if either A is true or B is true. And then here's the big one, V alpha. That's the set of all states where no matter how you run program alpha from X, you always end up in a state where A is true.
There's also this really handy notation, Langle alpha wrangle A, which is just shorthand for Gil not alpha act. So instead of saying in every possible way, alpha could run is true afterward, it's saying there's at least one way to run alpha, right, so that A is true afterward. So alpha is like saying something's necessary, it's got to happen, and Langle angle is like saying something's possible, it could happen.
Exactly. And there are some like fundamental truths about these program constructs and modalities that hold no matter what LTS you're looking at, like alpha beta is logically the same as alpha beta, which makes sense, right? If A has got to be true after running alpha and then beta, it's got to be the case that after running alpha, it was already guaranteed that A would be true after running beta. Similarly, alpha cup beta is the same as saying both alpha and beta have got to be true because A has to be true after either alpha or beta is run.
The axiom for iteration is particularly interesting. Alpha, left, right arrow, A, land, alpha, alpha. Basically, this is saying that A is true after doing alpha any number of times, even 0 times, if and only if two things are true. 1, A is true right now, and 2, after doing alpha once, A will still be true after any number of further repetitions of alpha. It's kind of like that domino effect, right? And then for the test, AB is the same as just saying A, right arrow, B, which makes sense. If A is true and the test lets you continue without changing anything, then B better be true as well.
These, what we call valid formulas, they give us a solid set of rules for logically thinking about how programs behave. Now, say we've got two different LTSs. How do we know if they act the same from the perspective of PDL? That's where B simulation comes in.
Ah, by simulation. It's like a way of saying two systems are basically the same in terms of what PDL can tell us about them, right? How exactly does that work?
Right, so a bisimulation between two LTSs, let's call them M and M, is a relation, a set of pairs, that connects states in to states in M. We write it as Z. So if a state in F is related to a state written, then three things have got to be true. First, got to have the same atomic propositions that are true in them. Second, for every atomic program, say pi, if you can get from X to some other state, Y, by doing pi, then there has to be a matching transition from some state, Y's in the same pi, have to be related by Z as well. And third, the same thing has to work in reverse. If there's a pi transition from Y, then there's got to be a pi transition from X to some Y, such that Y are related by Z. It's like they're mirroring each other step by step, both in terms of what's true about them and what actions they can do.
Sounds like a pretty strong notion of equivalence, not just looking at where they end up, but how they get there too.
Exactly. And the really cool thing is that if two states in two different LTSs are B-similar, then they satisfy the exact same PDL formulas. That means PDL can't tell them apart. And all those program operations we talked about, sequence, choice, iteration, and test, they all preserve B-simulation. So if you start with B-similar states and you build up programs using those operations, you'll always end up with sets of states that are still B-similar. PDL basically respects this fundamental way of saying two systems are the same.
Okay, let's just take a second to let that sink in. So simulation gives us a really solid way to say when two models of computation are the same in terms of what PDL can observe about them. It's like a way of ignoring all the little details that don't matter and focusing on the core behavior, almost like a philosophical idea of what it means for two programs to be identical in how they act.
Exactly. Now, moving on from what PDL means to how we can actually reason within it, let's talk about proof theory. The whole point here is to come up with a set of axioms, things we just accept as true, and rules of inference, ways to get new truths from old ones. What we're trying to do is make a system where we can formally prove a statement, written as V-A, if and only if it's logically valid, written as models A, which means it's true in every possible LTS.
And like we mentioned earlier, PDL builds on good old-fashioned propositional logic. So all the usual tautologies and rules like modus ponens, which says if A is true and A implies B, then B must be true. They're all part of the system. Plus, for every program, alpha, we've got what's called the distribution axiom, written as K. Alpha A, right arrow, B, right arrow. Alpha A, right arrow, alpha B. So it's saying if after running alpha implying B is always true, and if after running A is always true, then after running alpha must also always be true.
Then we've got the necessitation rule, N. If you can prove that a formula A is just plain true no matter what, then you can say that alpha is also true no matter what state you start in. These two, K and N, together with all the rules of propositional logic, they make up what's called a normal modal logic. And PDL is what's called a multimodal logic because it has a modality for each program.
So on top of that, PDL has some specific axioms for each of its program constructs, like A1 for sequence, alpha, beta, A, left, right, O, alpha, beta, A2 for choice, alpha, cup, beta, left, right, arrow, alpha, land, A3 for unbounded iteration, A land, alpha, alpha, A4 for the test, AB, left, right, arrow, A, right, arrow, B. These axioms basically put those fundamental relationships we talked about before right into the proof system.
And to deal with unbounded iteration, we need a rule that captures this idea of potentially going on forever. That's where the loop invariance rule comes in. It says if we can prove that a right arrow alpha, meaning that if A is true before running alpha once, it's still true afterward, then we can conclude a right arrow alpha, meaning if A is true before running alpha any number of times, it's still true afterward. It's all about things that stay true even when you loop.
Interestingly, this loop invariance rule can also be written as an axiom called the induction axiom at A5, a land alpha, a right arrow alpha. This way of writing it might remind you of mathematical induction, where you prove a base case and then an inductive step to show something's true for all natural numbers. Here, we're doing the same thing, but for the number of times a loop runs.
That's a great point. Coming up with a complete set of axioms using A1 through A5 and rules like Kn and modus ponens to capture all the truths of PDL, that was a huge accomplishment. People like Segerberg and Parikh did a lot of important work on that. They showed that this system is sound, meaning anything you can prove in it is actually true. And they showed that it's complete, meaning anything that's true can be proven within the system. So it's like a perfect match between our rules for proving things and the actual truths about programs.
It sounds like it must have been really hard to prove completeness for a logic as powerful as PDL.
Oh, it definitely was. And since then, people have come up with different ways to axiomatize PDL. One that's particularly interesting uses what's called an infinitary rule. It's called IAOA. It basically says if you can prove beta alpha A for every single natural number, n, meaning after running beta, and then alpha m times, is always true, then you can conclude beta alpha, meaning after running beta, and then alpha any finite number of times is always true. So you're basically looking at what happens after every possible number of loop iterations all at once, even though there are infinitely many of them. And this system, with this infinitary rule and the usual axioms for sequence, choice, iteration, and test, it turns out to be sound and complete too, and it gives you the same set of valid formulas as the original system.
All right, so we've got a decent handle on what PDL lets us say and how we can actually prove stuff in it. But from a computational perspective, there's a really important question. Can we actually figure out, decide whether a given PDL formula is satisfiable? That means, can we tell if there's at least one state in at least one LTS where that formula is true? That's the PDL SAT problem.
That's the million-dollar question, right? Now, with a sound and complete system like the ones we've been talking about, you might think, okay, let's try to prove the negation of the formula. If we can do that, then we know the original formula can't be true. But here's the catch. If we can't prove the negation, That doesn't automatically mean the original formula is satisfiable. It might just mean we haven't found the right proof yet.
Right? Just because we can't find a proof doesn't mean there isn't one out there somewhere.
Exactly. But there's a key result for PDL called the finite model property. This says that if a PDL formula can be true at all, then it can be true in an LTS that has a finite number of states. That gives us a way to, in theory, check for satisfiability. We could list out all the finite LTSs and see if our formula is true in any of them. If we find one, then we know it's satisfiable. And if we can somehow check all of them and don't find any, then we know it's unsatisfiable.
But that sounds like it could take forever. I mean, are there infinitely many finite LTSs?
You got it. There are
Yeah.
infinitely many. But luckily, there's a more powerful result called the small model property.
Huh.
It says that if a PDL formula, let's call it A, is satisfiable, then it's satisfiable in a finite model whose size, the number of states, is at most exponential in the length of the formula. So that gives us a limit on how big the models we need to check are. It's still a lot of models to check, but it's a finite number.
Okay, so at least theoretically, we could just generate all the LTSs up to that size and see if the formula holds in any of them. Still sounds like it would take a long time, especially for formulas that are even a little bit complicated.
Absolutely. And in fact, Fisher and Ladner did some groundbreaking work on this.
Hmm?
They figured out that PDL SAT, this problem of deciding whether a PDL formula is satisfiable, is what we call XPT time complete. That means it can be solved in exponential time, but it can't be solved any faster than that. So it's definitely a hard problem, but at least we can solve it, at least in principle.
This is all really interesting. So we have this logic, PDL, that can talk about all these complex behaviors of programs, and we have this really solid system for proving stuff in it. And we even know exactly how hard it is to figure out if a statement in this logic can even be true. It really shows how connected logic and computation are.
And, it's worth taking a step back to see where this all came from historically. Why were people even interested in these logics of programs in the first place? Well, it all started from this need to really understand what programs mean and to make sure they actually do what we want them to do. People like Floyd and Hoare, they were real trailblazers in this area of formal methods for program verification. In particular, Hoare came up with this really elegant way of reasoning about programs using what we call Hoare triples, statements that look like this. What this means is if precondition is true before we run program alpha, and if alpha actually finishes running, then postcondition B will be true afterward.
Oh, those are the famous Hoare triples, right? They're like the bread and butter of formally specifying and verifying programs.
You got it. And the cool thing is, there's this direct connection between these Hoare triples and formulas in PDL. A Hoare triple corresponds exactly to the PDL formula A right arrow alpha B. So what that PDL formula is saying is, if A is true at the start, then after every single way that alpha could run and finish will be true.
Huh.
Pratt was the one who really made this connection clear, and it's a big deal. It showed that PDL could be the underlying logic for verifying programs.
And it's not just a superficial connection, right? You mentioned that PDL kind of generalizes Hoare's logic. How so?
Right, all those basic rules that Hoare came up with for reasoning about programs, you can actually derive them as theorems within PDL. For example, Hoare's logic has this rule called the rule of composition. He says if you can prove alpha 1b, then you can also prove alpha 1, alpha 2. Now, if we translate that into PDL, it means that if A right arrow alpha 1b and B right arrow alpha 2c are both true, then A right arrow alpha 1, alpha 2 must also be true. And you can prove that using the axiom for sequential composition in PDL. Alpha 1, alpha 2c, left right arrow, alpha 1, alpha 2c.
That's a pretty strong link. It's like PDL is this deeper, more powerful logical framework that explains why those rules that Hoare came up with actually work. Like, we've found the underlying laws of physics that explain why those rules of thumb work.
Exactly. And PDL can actually define a lot of those common programming constructs we use all the time, like if-then-else statements, while loops, repeat until loops, as well as things like abort, which just stops everything, and skip, which does nothing. You can define all of these in PDL using just sequence, choice, iteration, and test. For instance, an if A, then alpha else beta statement can be written in PDL as A, air, beta. That shows how flexible PDL is. It can actually model those control flow things we see in real-world programs.
So PDL isn't just some abstract logic that's only good for theoretical discussions. It's actually really closely tied to making sure that computer programs do what we want them to do in practice.
That's an important point, but there's something important to keep in mind. The way Hoare originally set up his logic, it mainly deals with what's called partial correctness. It says, if a program finishes, then the postcondition will be true. but it doesn't actually guarantee that the program will finish.
Ah, yes, the age-old problem of infinite loops.
Exactly. So to talk about total correctness, which means the program does what we want and it actually finishes, we need to go beyond basic PDL. For programs that don't have any choices to make, if we can prove A right arrow alpha wrangle B, then that means there's at least one way to run alpha that ends in a state where B is true. And since it's deterministic, there's only one way to run it, so it must finish and lead to B.
But what about programs that do have choices? Or in general, how can we prove that a program will always finish running?
Yeah, for a more general way to handle total correctness, we need a more powerful logic than basic PDL. That's where our PDL comes in. It stands for Propositional Dynamic Logic with repeating. It's basically PDL, but with this new operator, delta alpha, which is true in a state if you can run alpha forever without starting from that state.
So delta alpha is a way of saying, hey, this program might just keep going and going.
Exactly. And using that, we can define this thing called infidi alpha, which tells you whether program alpha could run forever. For instance, infidi alpha is true if there's a way to run alpha some number of times and end up in a state where you can then run alpha forever.
And then we can express total correctness in RPDL like this. A right arrow, L not in 50 alpha. This is saying if A is true at the beginning, then alpha won't run forever, and every way of running alpha that does finish will end in a state where B is true. It combines both of those requirements, doing the right thing and actually finishing.
That's right. RPDL gives us a formal way to talk about both what happens when a program ends and whether it even ends at all.
It's clear that PDL, even in its basic form, has been super influential, but it's also amazing how people have tweaked and extended it to look at different aspects of computation. It's like this core idea that's branched out into all these specialized areas.
Absolutely. Researchers have come up with a ton of variations of PDL by adding or removing stuff from the original framework. For example, there's PDL without tests, sometimes called PDL-0, which just uses sequence, choice, and iteration of atomic programs. What's interesting is that regular PDL is actually more powerful than PDL-0. There are things you can express in PDL that you just can't express in PDL-0, which shows how important that test construct is.
That's pretty wild. It shows how even something as simple as an if statement can really change how much you can say about programs and a logic.
Exactly. Then there's PDL with converse, or CPDL, which adds this operator, alpha 1, that represents running program in reverse. So now you can talk about what must have been true before a program ran, not just what's true afterward. CPDL is definitely more powerful than PDL, but amazingly, it's still XP time complete, just like regular PDL.
So even though you can talk about more things, it's not actually any harder to figure out if a formula is satisfiable. That's a pretty neat balance.
It is. And then there's SLPDL, which stands for Propositional Dynamic Logic, with a strong loop predicate. It introduces this thing called maths loop alpha, which tells you if a program alpha can loop back to the same state in one step. Now, what's weird is that SLPDL doesn't have the finite model property. Some formulas can only be true in infinite models. But even so, figuring out if a formula is satisfiable is still decidable in exponential time.
That's a strange combination, right? You need infinite models, but you can still decide satisfiability pretty efficiently. It shows how subtle the relationship between expressiveness and complexity can be.
For sure. And then there's PDL with intersection, or IPDL, which adds this new program constructor, alpha cap beta, that basically means you only take a step if both alpha and beta can take you to the same next state. It seems really useful for modeling things like concurrent systems, where lots of things are happening at the same time.
It does sound like a useful tool for thinking about how things interact in those kinds of systems.
But it comes at a price. IPDL is a lot more complex than regular PDL. It doesn't have the finite model property either, and figuring out if a formula is satisfiable is 2 XP time complete. That's even harder than XP time complete. And if you add converse to IPDL, you get ICPDL, which is also 2 XP time complete for satisfiability. It actually took a long time for people to even figure out how to axiomatize IPDL.
So we have this whole family of dynamic logics, each designed to capture some aspect of computation. It's amazing to see how far people have taken this idea.
Absolutely. PDL and all its variations give us this incredible toolkit for understanding how dynamic systems, especially computer programs, behave. They let us be really precise about how programs run step by step, how they make choices, how they repeat, and what it means for them to be correct. And for someone who's into philosophy and wants to understand what computation really is, these logics provide a rigorous and insightful way to think about it as this logical process unfolding over time.
So, as we wrap up this deep dive into PDL, it's clear that it's way more than just a tool for computer scientists. It's a really profound formal system that lets us reason about all the dynamic stuff that goes on in computation. We've seen how it connects to ideas like program correctness and termination, and we've seen how people have extended it to explore all sorts of different aspects of computation. In the end, PDL gives us this precise way of capturing how programs change the world, or at least the world of computational states.
And to our listener, thinking about things philosophically, it's pretty mind-blowing how these basic philosophical ideas of necessity and possibility show up so clearly in PDL, with the alpha operator for necessity and the alpha angle operator for possibility. What does that tell us about how action and change work? Not just in computers, but maybe in the world in general. How do these formal systems like PDL help us understand and model all the dynamic processes we see around us? It's a question that really brings together logic, philosophy, and computer science. And it's something we're thinking about long after this deep dive is over.